2021 question number 2. This is a great question. I really love this question. It's a classic example of the Olympiad sort of partial question writing philosophy of taking something that's incredibly simple and making it look initially quite complicated, and it's just about whether or not you can sort of decode the pattern behind what you're looking at. So when you first see this diagram, it looks complicated, but actually the point of this diagram is to make it look really, really simple. And once you've sort of understood what's happening in this diagram, the whole thing sort of unlocks. And even when they give you the more complicated scheme here, this also becomes very, very simple. You know, students get very bogged down in sort of going, oh, what's going on here? How is this going around here? But really, you need to see what the overall picture is. So the first question is, write an equation for the main reaction in the carbonator. So if we look just at the carbonator, we look what's going into the carbonator. Calcium oxide is going in. Flue gas is going in. That's got carbon dioxide in. It even tells you that's the important thing that's going in. And then out of the carbonator is clean flue gas. So the carbon dioxide is being used up inside the carbonator, and then calcium carbonate is also coming out. So the two things going in are this, and the thing coming out is this. Okay, so let's just first write that down. So we have CaO plus CO2 becomes CaCO3. And I feel like if you can get that first equation, you'll see just how to read this diagram. And then that makes sense, right? So what the idea is, this is carbon capture. Okay, so calcium oxide is used to react with the dirty flue gas. So flue gas is just like exhaust gas, right? So it's got carbon dioxide in it. So you put it in, the carbon dioxide reacts with the calcium oxide, it produces calcium carbonate, and then the flue gas goes out, but now it's clean because the carbon dioxide is now locked into the calcium carbonate. And that's the entire point. Okay? Then it says, write an equation for the main reaction in the calciner. So we just apply the same logic. So it's just going to be, well, what's involved? So the first thing that comes in is CaCO3. So that's my reactant. CaCO3. Any other reactants? No, but there are two things coming out. Well, there's my CO2 coming out for storage and my CaO going back into the carbonator. So it's just the opposite. Okay, so you see, this diagram is actually very, very useful. It makes the whole process much, much simpler to understand. One of the impurities in flue gases is sulfur dioxide from the combustion of sulfur-containing fuels. This can react in the carbonator to form an unreactive impurity which can accumulate over successive cycles and reduce the efficiency of the process. Okay, so what we're having is we're producing sulfur dioxide in here, and the sulfur dioxide is reducing the efficiency of this process by reacting with something. Okay, write an equation for the formation of sulfur dioxide from the combustion of hydrogen sulfide. So we have H2S, combustion gives me O2, gives me sulfur dioxide, SO2. Now obviously there has to be another product with hydrogen in. And I think that most students here will look and they'll go, well, I've got one sulfur here, I've got two oxygens here, two oxygens here, and I've got two hydrogens left over. So most students are going to write down H2. Which means that then they're applying the law of conservation of mass, fine, but they're not applying their chemistry knowledge sufficiently well, because this is a combustion reaction. In a combustion reaction, you're not going to produce a highly combustible product. It just does not make sense that if I'm burning this, I'm going to make something that burns very easily. All right, so this is oxidation. Oxidation of the sulfur, oxidation of the hydrogen. So the other product will be H2O. Okay, and you should know that, because if you were to write CH4 plus O2, you're never going to write the products of that as CO2 and H2. Okay, makes no sense. All right, you know it has to be water. All right, so then all I've got to do is balance it. So I've got one sulfur, two hydrogens, and I've got three oxygens here. So I'm just going to do 3 over 2 there. Okay. And then Another equation, write an equation for the reaction of sulfur dioxide with calcium carbonate and oxygen to give two products. So it's sulfur dioxide, calcium carbonate, and oxygen. Okay, so sulfur dioxide, SO2, plus calcium carbonate, CaCO3, plus O2, to give me two products. So I know that one of them is going to be an unreactive impurity. And looking at this, it's going to be a calcium salt that is going to sort of mess up my process, because my calcium carbonate is being the calcium salt here has been recycled. Yeah, I make calcium carbonate, then I make calcium oxide, then I make calcium carbonate, then I make calcium oxide. If I make another calcium salt, it's going to mess it up. So what other calcium salts do I know that I can make from here? Obviously calcium sulfate, CaSO4. And if I use up my sulfur and I use up my oxygen, I'm left with carbon and oxygen. So my other product is going to be CO2, which is not great because I'm supposed to be storing my CO2, not producing more CO2. So let's balance it. One calcium, one sulfur, and then I've got 1, 2, 5, 7 oxygens. I've only got 6 here, so I can just put a half oxygen there. Fine. Okay. Then we have this more complicated direct air capture process, and again, it's not worth trying to understand what's going on. Don't look at this and think, oh, I first need to understand this diagram before I can possibly move on. No. What's the question? Write an equation for the reaction that happens in the pellet reactor. Here is the pellet reactor. What's going in? This goes in. This goes in. Yeah. In. This comes out. This comes out. That's the purpose of this diagram. So I'm going to write it down. So I've got going in K2CO3 and calcium hydroxide. And then coming out, I've got my potassium hydroxide and calcium carbonate. And if there was anything else, they would write it on the diagram. So you know that that's it. Okay, so then let's just balance it. Two potassiums here. One calcium, that's fine. One carbon. Two hydrogens. And then 3 and 3 and 2 and 2. Okay, so it's fine. Balance like that. All right. Then it says, calculate the standard enthalpy change for the reaction which occurs in the air contractor. So here's the air contractor, and it actually even tells you. I've just realised the first time I did this, I didn't even see this equation. So I worked it all out myself, what the equation was using the arrows, but it actually tells you. And you can see that lines up, right? Because there's CO2 coming in, that's coming in here. There's potassium hydroxide coming in, that's coming in here. And then there's water going out, and there's potassium carbonate coming out. So the point is that this one you ignore, right? Because even though it says air is coming out, the important point is that there's no CO2 in the air that's coming out. So there's CO2 going in, which is why it's in the reactants, but the air that comes out is clean, which is why there's no CO2 in the products. The CO2 is now captured in the potassium carbonate. Anyway, let's write the equation out. So it's CO2 plus 2KOH becomes H2O plus K2CO3, and its enthalpy, you're given standard enthalpies of formation, so it's just going to be delta H for the reaction is going to be delta HF of the products minus delta HF of the reactants. So then I just do the maths. So the products are water and potassium carbonate. So it's going to be minus 285.8. I'll write it out. This is going to be equals to minus 285.8 plus minus 1151.2. Subtract carbon dioxide, which is minus 393.5, plus 2 times minus 4 to 4.8. Now let's do all the maths. So we get that, take 1151.2 plus 393.5 plus 2 times 4 to 4.8 gives me minus 193.9. Minus 193.9 kilojoules per mole. And then the last two questions are: tick the correct statement that describes the standard enthalpy change at 298 K for the sum of the reactions in the 4 reactors. So this part here tells me that in here I've got minus 193.9. Now, if you wanted to waste a lot of time, you could work it out for this one, you could work it out for this one, you could work it out for this one, and you could add it all together. Or there's going to be an easier way of doing it. So I've already said I ignore this one here. I ignore the CO2 coming out because it says there's no CO2 coming out. So what I've got going in is I've got CO2. So I've got CO2 coming in, and I've got H2O coming out. And over here, I've got CO2 coming out, and I've got H2O coming in. So you can see that the whole process, nothing happens. I put CO2 in here, I put H2O in here, I get H2O out here, I get CO2 out here. There's no overall change in this process. The entire point is that the only change that's happening is that the CO2 that's coming in here is CO2 in air, and the CO2 that's coming out here is CO2 for storage. But because of the first law of thermodynamics, if all of my which underpins all Hess's law, because there's no overall change in the reactants and the products, then there's no overall energy change, right? So if you were to work out what the enthalpy change was here, enthalpy changes here, enthalpy changes here, and add them all up, it would all come to 0. So the standard enthalpy change is 0. Then we are asked a slightly more difficult question about the entropy changes. Okay, and it says tick 2 correct statements. So one statement is about the universe, one statement is about the process. So I just said that the only change that's happening is that carbon dioxide in the air is going into carbon dioxide for storage. Now, it should hopefully be fairly clear that that process is going to be a negative entropy change, that carbon dioxide in the air is going to be more disordered than carbon dioxide that's going to be in storage. Okay, so we know that the entropy change for the process is going to be negative. Then it's up to you. Actually, the first time I did this, I did this one first. If the process is negative, then the universe is positive. But you could do it. The other way of doing it is you should just know that any process, the entropy change. So for any overall process, the entropy change of the universe will be positive. It's not possible to do this and have an overall universe negative entropy change. The entropy change of the universe must always be positive. So hopefully that makes sense. This comes down to your understanding of entropy, really. But I feel like as far as entropy questions go, it's a really nice question, but and it should be fairly straightforward.